So today, Johnny and possibly his colleague Stefanos are going to be talking about exact contraction of tensor networks.
Yeah, so thank you very much for inviting me to talk. I'm going to talk about exactly contracting tensor networks. So kind of a smaller subfield of the whole area of tensor networks, and just a kind of tour of various different bits of the technology that you can use to contract tensor networks exactly. And this is mostly work, well, almost entirely work with Stefanos Cortis in this archive paper here, which hopefully tomorrow should be fairly majorly updated. Is my computer working? Okay, yeah, so I'm kind of assuming everybody knows what tensor networks are pretty well. At any point, please do jump in with questions, but just to set kind of a general context for this, tensor networks we think of as these kind of simple local rules describing how you contract tensors with a very nice graphical interpretation. So, by summing over indices, you can create edges and vertices and embed this in some potentially much larger graph G. And while this seems like a kind of, trivial thing to write down graphically, as soon as you get to these incredibly large objects, you're representing kind of exponentially complex sums or overall objects. And you can write this tensor network contraction fairly simply in this way, where it's just some product over entries of tensors in this graph, each node being a tensor, and then some sum over exponentially many strings indexing every single edge in this tensor network. And the power of tensor networks, like I said, is very much to do with the fact that we're representing some kind of exponential sum here. And there's lots of different things you can put in these T tensors in order to make the overall object represent something different. And very roughly, maybe in quantum computation, we think about these gates, these tensors being either gates or states. In like a many-body quantum ansatz, we might think of them as being like virtual Hilbert spaces, and the tensors project these entangled pairs down to some other degrees of freedom. But you can also just replace these with kind of local constraints, clauses that denote some kind of satisfiability constraints. And you can see if this is a big product, so you're basically requiring, by timesing all of these things together, that every single constraint is satisfied. And then classical stat mechanics, these tensors represent kind of local energies. And by summing over maybe the exponential of these energies, you have a direct way to compute partition functions. And then finally, there's all sorts of use for these. The final one might be inference, where each of these is some kind of conditional probability distribution, describing a very complex network of kind of phenomena that you're trying to marginalize over. And it's kind of interesting in itself that tensor networks can represent so many things, but I guess just as importantly, like all of these are fairly useful practical things to do that people are trying very hard to solve computationally. So exact tensor network contraction is the kind of the simplest way of trying to compute with these things, where you actually are really trying to exactly represent this sum and compute what its overall value. And while this is like some kind of incredibly memory efficient representation of very, very complex objects, kind of naively contracting it is this, like I said, exponentially slow sum that you never actually want to do yourself, probably because you're really enumerating over exponentially many combinations of strings. But we can make use of associativity to bubble these tensors and essentially pairwise project them into much, well, hopefully smaller intermediate tensors. And while we still expect this problem to be exponentially scaling, even in the best case, so even if you find some kind of optimal way of doing this for a generic graph, we know by this result from Markov and Xi that we're still going to kind of the best we can do is generically exponential in the tree width of the line graph. Nonetheless, the cost of choosing one of these bubbling orders is like extraordinarily sensitive to the order we do it in, and so we can shave off these like huge exponential factors from the runtime of trying to exactly enumerate those things by very cleverly trying to confine contraction orders for tensors. So just to give a nice construction which really describes exactly the costs involved of performing a exact contraction. If we have some graph describing a tensor network G, and each of these things down here is the just the set of indices on an initial tensor, then the kind of computational space and time of actually contracting this is given by this contraction tree. And this is something you can, very simply check the costs of if you construct it ahead of time. You basically, the indices from each of these leaf tensors travel up through the tree, and at each vertex in the tree, they either kind of annihilate or continue. And based on the vertex congestion, so just the number of indices passing through this, you have like an exact expression for the number of flops associated with multiplying those two tensors together. And each of these vertices also corresponds to like a bipartition of our original graph G. And then you can also think about the sizes of the tensors, which is just given by the edge congestions. And each of these is like a subgraph of G. And this is like a really kind of neat and feels like not very reducible way of denoting a tensor network contraction that is indeed a nice thing to try and directly construct and optimize when you're contracting tensor networks. So in this original definition, I put this XU here, which is kind of like some substring of all of these index permutations that we're indexed as an individual tensor. And in this definition as well, we just have indices kind of flowing up this tree. And neither of these things preclude indices appearing on at least 3 or basically as many tensors as we want. And I'm going to call these hyper edges. They're, in lots of other contexts, they're called different things. So you can think about there just being an implicit copy tensor here. So here's just a very small example of a hypernetwork where we have some index H, which is shared by 4 tensors at once. This is also like a Z spider from ZX calculus. You can take a line graph of a hypergraph and all of these edges have just become regular nodes again, so it's no problem representing them in that way. And you can also think about this as this canon parafact decomposition, which is a kind of low rank decomposition of tensors that is used sometimes. And this is a useful abstraction because now we're really saying we can try and contract anything of this form. There's no constraints on how the indices appear. So like maybe in a standard tensor network, you might think of requiring that every index appears exactly twice or once. And this is just quite a natural way to extend that, where the tensors still live on the nodes rather than having some kind of dual representation. So now all of the costs for contracting are really associated with partitioning a hypergraph rather than just a normal graph. And when we perform these contractions, rather than being some kind of matrix multiplication, it's like a mixed kind of Hadamard in a product. So like a batched matrix multiply. And that's, practically speaking, that's very efficient still. So just to kind of quickly illustrate or to think about what's the benefit of doing these when we could, in fact, just insert, for example, an actual copy tensor. So, actually inserting a full copy tensor, if it was dense, would be potentially some incredibly large, rank number of indices tensor that we would want to do. But kind of in comparison to like the rules with Z spiders, you could just decompose this into as many order 3 copy tensors as you want. For example, some kind of tree copy tensor or an MPS. And while this notion can keep the kind of scaling of the contraction complexity, it loses some of the kind of natural permutation of symmetry of hyperindices. So now the best way to create like some kind of hypergraph decomposition that preserves the rank across all of these cuts now depends on how we're going to contract it in the end. So we're kind of jumping the gun slightly if we insert these eagerly. And so the way to think about this hyperedge is if you cut them in half, and cutting in half is kind of how what we're going to use as a proxy for the exact contraction costs. These have the same cut weight regardless of how you partition them. Whereas if you insert some kind of, this would be like kind of GHZ state, then now whenever we partition it, there's only some cuts which are going to have the same rank as the hyperindex. So just as like a very extreme example of this, if we take the Ising model on a like all-to-all interaction graph, so that's just taking this graph and inserting a matrix like this on each of the edge, which describes the energy between two sites. The standard way of approaching these partition functions tensor networks would be to take the square root of this and absorb each factor into the vertices, and then your tensor network has exactly the same geometry as the underlying physical graph. But you can also just leave these hyperedges out lazily, represent this thing as a hypergraph, and you get like a drastically different scaling in terms of contraction complexity for this model, which is just to say that it's not like a kind of minor advantage having not representing these indices as hyperindices. It's potentially like a really significantly computationally advantageous thing to do.
Hey, Johnny.
Mm-hmm.
Is there any particular reason you still talk about cutting in half rather than cutting into arbitrary numbers of partitions at these hyperedges?
Well, because it's always like a recursive bipartition of the graph. So rather than cutting it into many parts at once, in the end, what it always comes down to is cutting the graph in half and then taking the new subgraph as a new tensor network and cutting that in half.
Okay.
So
it's more of just a way of organizing it rather than you're losing any generality there.
Yeah. In fact, you can always show that if you take some kind of tree which isn't like a bipartite tree like this, so maybe you contract 3 things at once, it's always more efficient to make it into a bipartite tree where everything is pairwise, which corresponds to always cutting your graph in half when constructing these contraction trees. So that's like the kind of context of these hypergraph contractions. Like the big question is, like, rather than just blindly doing these big exact contractions on tensor networks, can we kind of motivated by what we know are the costs of the exact contraction and a few other things, can we try and locally transform the tensor network first to make it really as minimal as possible? So, you know, we would like to reduce the number of tensors. We're very happy to introduce hyperedges because we can handle those well. We know they're pretty efficient. And our overall aim is to kind of reduce the weight of these hypergraph cuts. It's kind of slightly ill-defined because we don't know what the full cost is until we have the entire tree, but we know roughly that there's many kind of operations that can only reduce the weight of a hypergraph partition. And so these are kind of useful things to do. And we take a fairly kind of computationally direct approach to doing this. We're kind of expecting there still to be some tensor network left over by the end of this simplification process. So maybe unlike some other more, well, there's these other approaches here, which I'll just mention briefly, where the aim is really to like completely, fully simplify a tensor network. And I'm sure this is a very incomplete list, but a very early instance is this holographic algorithms paper of Leslie Valiant, where the kind of internal values of the tensors are somehow very closely related to some weights you can assign to the edges of the graph. And once you have that, once you've reduced or mapped, locally transformed your tensors into those values, you can actually compute the whole sum as the Pfaffian of the adjacency matrix. And this approach was extended by Bravi to the non-planar case. And then, of course, ZX calculus, there's several different types of circuits which have been shown you can kind of completely, fully simplify to some trivial value at the end. Clifford stabilizer quantum circuits, and also these Zorsat instances where the kind of local constraints you put are really on parity, so whether you have an even number of odd local constraints. So we know that there are instances where, without kind of considering the entire structure of the graph or considering it in some simple way, tensor networks can be drastically reduced in their complexity. So the approach we took was, and this is mostly motivated by quantum circuits, so those are mostly the examples I'll give, is just to really introduce a load of basic rules based on the entries of the local tensor structures, and then just figure out some very simple ways to try and manipulate the tensor network structure based on these. So the basic simplification that doesn't involve what's inside the tensors in tool is this rank simplification. When I say rank here, I really mean just the order of the tensors, the number of dimensions. So here you can take your very large graph of tensors, and you can just very quickly iterate over all of the tensors and find any pairwise contractions that don't produce larger rank tensors than the two inputs. And this is basically like a kind of topology preserving simplification. All loops remain. You just get rid of all of these kind of dangly bits and long, slightly more complicated than that with hyperindices, but to first order, that's essentially what you're doing. And you don't need to know anything about the insides of the tensors. And a good example of this is if you're just doing a basic quantum circuit simulation, all of the single qubit gates are just rank 2 tensors, so you can essentially for free absorb as many of those as you want into their nearest neighbor tensors. Then the next very simple rule we might think of is this column reduction. So this is the first kind of rule that you'd think about looking inside a tensor. And you can just search tensors for 0 entries, and if they're basically all 0 apart from one column, for example, this tensor T has some axis index IX joined with several other tensors. And then this is super trivial. If there's only one value this index can take with respect to T because all of the other values are 0, then you can basically annihilate this index from the whole tensor network. You can introduce this basis vector tensor and absorb it into every tensor that shares this index. And obviously this, you'd probably not by construction have tensors like this in your network, but in conjunction with some of the other simplification schemes, you find these tensors are produced, and therefore this is a useful way to simplify them further. And clearly, in this case, you can imagine, we can always choose some kind of bipartition here, which is exactly preserved in this case, and yet we've drastically reduced the number of tensors. And here, of course, we can only really have reduced the contraction cost by getting rid of an index. Then a slightly more advanced simplification that is more linear algebra inspired. You can just range over all of the tensors and check all bipartitions of the indexes. I'm kind of assuming these are all very small tensors still. And then if you find an exact low rank decomposition, you can just perform this decomposition. So now any bipartition that would cover this tensor now has a lower weight across. And this creates more tensors, which is not necessarily good, but they're usually lower weight cuts. And good examples of this are, if you're applying any kind of controlled gate, then obviously this has a rank 2 spatial decomposition, which is the the identity and the control signal basically from the source target to the target qubit. But if we're just doing this generically, we're not kind of putting in explicitly what space is, then you find things like the ISWAP gate has this swap spatial decomposition, and of course many tensors, especially when they're constructed from very structured constituents like clauses, have got low rank decompositions. And then another important one is this diagonal reduction. So here you just search tensors, and if you find any tensor which has a pair of diagonal axes, which are, well, they're diagonal, they're zero whenever the two indices are different. So the tensor can effectively be described as a tensor timesing a delta function. Then this is the point when you can introduce a hyperindex. So you can basically take the diagonal of this tensor, you can reduce it to a single index, and just by relabeling this anywhere, so essentially propagating the copy tensor through, you've now generated a hyperindex in your tensor network, which should be much more efficient to contract. So like any kind of controlled gate, you find that the control tensor, which is essentially just the rank 3 identity, is now going to be like a diagonal tensor that really produces some kind of permutation invariant index between 3 tensors. So this is where, even if you don't have hyperindexes in your initial tensor network, just by simplifying it, you can often introduce them, and you'd hope to do this significantly. We also have, like, there's tensor networks have a gauge freedom, which means you can apply any kind of local transformation on the bonds. And you could think about trying to introduce one to produce as many of these diagonal reductions as possible. And really the most simple thing you can think about is just permuting the indices. And of course, if in t equals 2, so mostly for quantum circuits, the only non-trivial permutation is just Pauli X operator. So you can search through your tensors, and if you find 2 indices that are anti-diagonal, you can just gauge this bond in between them, and now you can go back to this stage and create a hyperindex. And again, this is only useful in conjunction with doing these other simplifications in some kind of loop. And then finally, if you wanted to think about the first kind of like slightly non-local simplification, you can very easily like range across your entire graph, compute every single short loop, and then try and perform a low rank decomposition across all of the kind of connected bipartitions of this loop. And the intuition here is that you often have, kind of redundant correlations in the loop that once you actually sum together, you can describe much more efficiently. So this is something I've been exploring recently. It's not in most of the following results, but it's also an interesting step towards a kind of compressed contraction where you're really considering doing quite a significant contraction, and also how that's going to be simplifiable or compressible in the future. And so to actually perform all of these, you really just do them all in a big loop sequence until the number of edges and vertices in your graph converges. And this process is pretty stable in that you generally converge to one tensor network fairly fairly reliably, but the order of simplification does matter somewhat. There's some, there's a couple of different orders you can do that seem to lead to different endpoints in your tensor network. Yeah, and it's worth noting that in most of these, you do some kind of comparison to zero. So you need to put in some kind of tolerance. For these things I'm talking about, these are all just generally something incredibly small number. We're not trying to approximate anything about the tensor network. It's really just like exact simplifications. And so, yeah, like I said, whilst the aim of these is really just to prepare the tensor network for exact contraction, what we found was that actually there's huge reductions from these in lots of cases, and sometimes this should say sometimes to like just the trivial, like there's a surprising amount of cases where just combining them yields you like a single tensor at the end. They can reduce all the way fully simplifiable. So just to run through some various examples of kind of tensor networks and quantum circuits that do simplify.
Sorry, Johnny, before you continue, these methods, they work on any tensor, right? Not just one that is fully contracted. Like also if you have dangling indices to the outside, if everything that you described still works, right?
Yeah, sure. Yeah. I mean, the only thing you need to be careful about is that you don't want to remove the index by some method. But yeah, you just, as long as you put in some logic that preserves the outer shape of the tensors, then all of this works fine. Yeah, so I guess the best thing to do is to just run through some examples of different cases where these simplifications lead to either very large or small reductions in the tensor network complexity, and then kind of our ability to contract them afterwards. So a very seemingly trivial example, but it's still kind of impressive, I think, or tells us something about how these simplifications are working. Is just taking the norm of some, basically arbitrarily large unitary tensor network ansatz. So by unitary tensor network, I mean essentially a kind of quantum circuit style tensor network where every tensor is a unitary or isometric gate, and you have a very well-defined notion of a light cone. So this is an example of such a tensor network. It's just like a very deep, random, all-to-all circuit on 100 qubits. You wouldn't expect to be able to compute anything with this usually. But just applying these local simplifications, this whole thing naturally boils down to like a single tensor with the number 1. And of course, it's not that useful, right? We already knew that the answer was 1 just by construction of the ansatz, but it illustrates the logic fairly nicely. So just using a combination of these two simplification schemes at this kind of interface where the unitaries meet, you always have U and U dagger, and because contracting this doesn't lead to any blow up of rank, you perform it, and then even though it doesn't know its identity, what it does know is that there's some kind of low rank decomposition spatially, and then these tensors are just rank simplified, absorbed into the nearest neighbors again without any effect. And so this process just repeats efficiently forever until you get down to a single tensor. An example where you don't necessarily get that much from, yep.
What do you mean by light cone structure?
Oh, I mean, well, so if you start at a single qubit, then, and you perform some entangling unitary gate, then the light cone of that qubit is now that qubit and the qubit it's entangled with. Mm-hmm. And say you perform some more unitary gates, then you have this kind of expanding set of qubits, which is whenever the unitary acts on any qubits which have already been acted on, you get a larger light cone that kind of spreads out with the depth of the circuit. This is an example where the light cone cancels exactly, but you can imagine if you had some operators here, say you're computing a local expectation, it would only be the light cones outside of that and propagating some way back that disappear. So this is like the trivial example where everything disappears, but you still get this same kind of cancellation at the interface when you have just local operators and some of the, which it's more like the reverse light cone for local operators that cancels at this interface.
Right, I see. And that's, so you're saying you see in the tensor network basically canceling as much as possible. Like if I was looking at this as a person, I was just canceling unitaries wherever I could.
Yeah.
Makes sense.
Which I mean, it's not, you could, obviously, it would make more sense possibly to do this by hand if you know that your ansatz is unitary, but it's just nice that it finds it kind of automatically. So then, yeah, the kind of the opposite end of the spectrum is like computing amplitudes of really random circuits. So this is more results about our kind of our exact contraction capabilities, but we have two examples here. One is just a rectangular quantum chip, like a 7x7 qubits here with CZ gates. And of course, because these are controlled gates, they have a nice decomposition and produce a load of this kind of hyperindex style entanglement. And here we have contraction costs. It's kind of like a log scale, essentially the time complexity, the number of scalar operations you need to compute. An amplitude are very, very roughly marked to like do it on your laptop line, you know, if you had a few hours or something. And what's notable here is like these three methods all make use of the hyperindexes, and these three methods not so much. There's big separation between them. The hyper methods are like our recent contributions to these tensor network optimization schemes, but there's also our simplifications going on here. I guess what's notable is like up until a few years ago, it was thought that this kind of depth of circuit was out of reach even for supercomputers. So like the depth 40 circuit on 49 qubits. But the kind of this huge savings you can make just by simplifying the tensor network and finding a better scheme have brought this down by like, you know, orders and orders of magnitude. Still exponentially scaling, but really, really expanded the kind of size of things you can contract. And so, yeah, because of the CZ gates, these are quite amenable to these diagonal simplifications I talked about. And then for Sycamore circuits, partly because of this, the gates that were used by Google are these FSIM gates with like slightly tuned off from ISWAP. So there's not an exact low rank decomposition of them. So here, this is a case where the circuits are very resistant to any kind of simplification. All you can really do is absorb single qubit gates. And here's just a nice illustration of kind of how nice some of our contraction path optimizers are now. So this green one is the kind of best way we have of doing these contractions. And you can see it's orders of magnitude better than many other methods. And this yellow method was one of the methods they used and Google used in their paper to estimate classical cost, although not the only one. And you can see there's huge factors being able to, and this is very much in the realm of, you know, possible contraction. And if you've seen the archive the last few days, then, you know, people have basically taken these kind of contraction paths and performed them to actually notionally simulate the Sycamore circuits. The one thing I will say is it's like for very shallow circuits. So for circuits where the correlations really only have time, well, they don't even have time to spread around a loop. if you combine all of these schemes with the loop simplification, then you can actually fully simplify circuits, which is a nice result. And then, so, other circuits that are pretty simplifiable, but nonetheless still very complex. The quantum approximate optimization algorithm. In this algorithm, you both have to evaluate some energy first before sampling from your kind of tuned quantum circuit. And here again, the gates are the exponential in this ZZ operator, but of course this is still a diagonal tensor. It doesn't really matter what the entries are of the tensor. We can still make use of this diagonal reduction to produce hyperindexes. And similarly, this, like the mixing term, is some fairly simple tensor. Performing simplifications here is really changes drastically the size of circuits that you can address. This is like contraction complexities for different number of qubits on random regular graphs. Again, this is do it on your laptop line. And you can very happily simulate, 50 up to 1,000 qubits. It actually gets easier just because of the structure of the graph with more qubits for like fairly deep. So this would be like depth 12, very long range circuits to evaluate the energy on. And then maybe some more, to me at least, more surprising results to the simplification. So if you just take the quantum Fourier transform, this is almost fully simplifiable for doing some tasks. So if you take just a random product state, so it's important that it does in fact have support on all the input bit strings. It's not just a single bit string, which you'd think of as just being doing the classical Fourier transform. It really is a superposition of many states. And you take this as the input to the quantum Fourier transform with some relatively large number of qubits. It doesn't matter, it doesn't seem to matter too much how large. Then even after simplification, you get potentially this very, very large complex wave function that can't be simplified any further. But once you construct like marginals for this wave function, so you say, what's the probability of getting bit string on these 5 qubits given this prior result and these qubits traced out. Fairly surprisingly to me, all of the marginals in this kind of object really simplify all the way down to very, very simple tensor networks like this. Some kind of small constant or proportionality larger than the size of the marginal you're computing things for.
Johnny?
Yeah.
Maybe this is getting too much into the woods, but how do you take a marginal in your approach?
Just so you create the double sandwich of psi and its conjugate, and then you kind of have all of the indices at the interface, and either those are traced out, which are the ones you haven't measured yet, as it were. Either you cut them and fix them at certain values, which is like your result so far, or you take the diagonal of them, which is like extracting the diagonal of the remaining density matrix. So you either cut them, take the diagonal, or trace them, and that gives you a the probability distribution on some qubits given a prior result. And that's the way, if you want to unbiasedly sample from a tensor network, that's the way you do it exactly. I think there's lots of reasons to think you could do it approximately and use Monte Carlo, but generically sampling from tensor networks is quite a lot harder than other tasks, which is in some ways why the random sampling task for Sycamore, for example, is like a very natural choice to show hardness. And there do seem to be some basically numeric results about the quantum Fourier transform having low rank tensor network decompositions or approximate decompositions. But as far as I'm aware, this is not something that is like super easy to understand why this would be so easy to fully simplify down. And then just to give like a, you know, I talked at the beginning about how many different things you can apply tensor networks to. So one example of this, not a kind of non-quantum circuit example, where you nonetheless still have very weighted, you still have very structured tensor networks, is these weighted model counting. So you know, you're encoding a load of local constraints as clauses, and you're basically trying to count all of the different solutions. And a very natural extension to this is you weight each variable, saying if it is satisfied, then I add this to my weight, and if it's not, I have some other negative weight. And I think, you know, in a few papers, including one Stefanos wrote, they showed how to write these things as tensor networks, but I think notably they're very naturally described by hypertensor networks rather than just tensor networks. So the variables, which are the indexes, can appear in any number of clauses, so it's natural to think about them being hyperindexes. And even the clauses themselves, which you can, you know, you can put in many different Boolean functions, but a classic one which makes this problem still, you know, sharply complete is the OR clause tensor. So you say any one of the incident variables has to be true, and this tensor is just, you know, very simply described by many things, including an MPS. But you can also do this like parafact decomposition on it to create another hyperindex. And so these things are kind of very naturally these large hyper tensor network objects. And we tried applying this. In model counting, there's competitions, and we tried applying, you know, to get some kind of hard instances of the problem to see how far we could take this. We took these kind of 100 instances, which are notionally hard, from this recent model counting competition, and we found that really mostly by the simplification procedure, actually, 99 of these can be solved exactly. So I think in most of them, or at least the majority, they all simplify down either to a scalar or to some very small kind of core hypertensor network like this that we can then contract with very little effort at all. And this 99 compares pretty favorably with 69 for the next best competitor in this competition, this add MC exact counter, which is in lots of ways state of the art. So this is kind of like a surprising result and maybe like a promising direction for applying these hypertensor networks. And an illustration, I think, of trying to think about how to maximally kind of bake the hyperindexes into your representation of the objects. This is just a very recent incomplete kind of list of some literature that I think is notable, particularly for the exact contraction. Maybe people can come back to that if they want. And for me, the like interesting future directions, I guess, in relation to ZX calcs and stuff is working out maybe whether there's some more concrete ways to understand what the simplification schemes are doing. Interesting for me is whether you can leverage something like the ZX calculus to rewrite circuits where you're kind of, the metric is not necessarily T count, but something to do with how hard the final graph is going to be to exactly contract. And then I guess the main thing that I'm thinking about at the moment is, you know, how powerful are these methods when you really start to mix both the exact contraction and the simplification. At the moment, as I've presented it, it's kind of, there's this simplification scheme that you just do as pre-processing, then you contract. But obviously these things can kind of be mixed in time, as it were, and then actually approximating and doing compression. So while we know that these problems are kind of sharp-P complete exactly, really not much is known about how tricky they are to approximate. And of course, in most many-body quantum uses of tensor networks, the key step is really compressing and making use of some kind of effective boundary to perform the contractions accurately. And oh yeah, I'll quickly plug these couple of libraries if anybody wants to try this stuff. It should just really be a matter of calling something like tensor network full simplify in Quim, this library I maintain at Caltech, and also all of the contraction pathfinders you can find in Gotengra, which is also, you can reproduce some of the more recent results for simulating Sycamore, for example. And that's all I have. Thanks for your time.